Today we're going to explore one of the most fascinating phenomena in nanoscience, the Nanoparticle Memory Effect Paradox. This is a remarkable situation where nanoparticles remember their history even after being heated to temperatures that should completely erase all memory of their past. Let's start by understanding what we mean by the memory effect in nanoparticles. The memory effect refers to the observation that certain structural or magnetic properties of nanoparticles remain imprinted from their past, even after full thermal cycling that should theoretically erase any previous configuration. According to classical thermodynamics, when you heat a system above a critical temperature and then cool it down, the system should reach its equilibrium state with no memory of how it got there. But nanoparticles violate this expectation. This creates a paradox. How can thermal energy, which should randomize all configurations, fail to erase the imprint of past states? The answer lies in the unique physics of nanoscale systems. To understand this paradox, we need to visualize the energy landscape of a nanoparticle system. Imagine a multidimensional energy landscape where each point represents a different configuration of the nanoparticle. The vertical axis represents energy, and the horizontal axes represent various configuration parameters like atomic positions or magnetic orientations. In nanoscale systems, this landscape is characterized by multiple local energy minima separated by high energy barriers. These barriers are crucial for understanding the memory effect. The rate at which a system can escape from one energy minimum and transition to another is governed by the Arrhenius equation. Tau equals tau 0 times the exponential of EB divided by kBt. Here tau is the relaxation time. Tau 0 is the attempt time, typically around 10 to the negative 9 to 10 to the negative 13 seconds. EB is the energy barrier height. kB is Boltzmann's constant, and T is temperature. This equation tells us how long the system remains trapped in a particular energy minimum before it has enough thermal energy to overcome the barrier and transition to a different state. Let's work through a concrete numerical example to see how dramatic this effect can be. Suppose we have an energy barrier of 1 electron volt. This is a typical value for magnetic anisotropy barriers and magnetic nanoparticles. 1 electron volt equals 1.6 times 10 to the negative 19 joules. Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. The attempt time tau 0 is approximately 10 to the negative 12 seconds. At room temperature, which is 300 Kelvin, let's calculate the relaxation time. EB divided by kBt equals 1.6 times 10 to the negative 19 divided by the product of 1.38 times 10 to the negative 23 and 300. This gives us approximately 38.6. So tau equals 10 to the negative 12 times e to the 38.6, which is approximately 10 to the 5th seconds. That's about 1 day. This means at room temperature, the system would need about 1 day to escape from this energy minimum. For all practical purposes, the system is frozen in its current state. Now let's ask an important question. What happens when we heat the system to a much higher temperature? Suppose we heat to 600 Kelvin, which is twice room temperature. Now, EB over kBt becomes approximately 19.3. The relaxation time becomes approximately 0.2 seconds. Notice the dramatic change. Just doubling the temperature reduced the relaxation time from 1 day to a fraction of a second. This demonstrates the exponential sensitivity of the relaxation time to temperature. This is key to understanding the paradox. Now we can explain the mechanism behind the memory effect paradox. Real nanoparticle systems don't have just one energy barrier. They have a distribution of barriers with different heights. This shows a typical distribution of energy barriers in a nanoparticle ensemble. Some barriers are low, some are high, and there's a spread of intermediate values. When you heat the system and then cool it, only the barriers below a certain threshold are overcome during the available time window. The higher barriers remain uncrossed. This leads to the concept of blocking temperature, which is central to understanding nanoparticle memory. The blocking temperature T equals EB divided by kB times the natural logarithm of tau measurement divided by tau 0. Here, tau measurement is the experimental measurement time. Above the blocking temperature, the system is superparamagnetic and exhibits no memory. The thermal energy is sufficient to rapidly flip between states. Below the blocking temperature, The system is in a block state where its orientation or structure is frozen and memory is preserved. Let's consider a specific example with iron oxide nanoparticles, which are extensively studied for magnetic memory applications. The energy barrier for magnetic nanoparticles is given by E B equals K times V, where K is the magnetic anisotropy constant and V is the particle volume. For magnetite, K is approximately 5 times 10 to the 4th joules per cubic meter. Consider a spherical particle with diameter 10 nanometers. The volume is 4/3 pi r cubed, where r is 5 times 10 to the negative 9 meters. This gives us a volume of approximately 5.24 times 10 to the negative 25 cubic meters. The energy barrier is therefore 5 times 10 to the 4th times 5.24 times 10 to the negative 25. This equals approximately 2.62 times 10 to the negative 20 joules, or about 0.16 electron volts. If our measurement time is 100 seconds, we can calculate the blocking temperature. TB equals 2.62 times 10 to the negative 20 divided by 1.38 times 10 to the negative 23 times the natural log of 10 to the 14th. This gives us a blocking temperature of approximately 59 Kelvin. Below this temperature, the nanoparticle will retain its magnetic orientation. Now let's address the central question of the paradox. Why doesn't full thermal cycling erase the memory? The answer lies in the rugged nature of the energy landscape and the hierarchy of timescales. During thermal cycling, the system can easily escape from shallow minima, shown in red, but remains trapped in deeper minima with higher barriers, shown in green. This creates a partial memory effect. In real experiments, the heating time is finite. Even at elevated temperatures, the system may not have enough time to explore all possible configurations and reach true thermal equilibrium. The cooling rate is critically important. If you cool too quickly, the system gets trapped in whatever configuration it had at high temperature, preserving structural features from the heating process. The memory effect isn't limited to magnetic properties. It also appears in structural configurations of metallic nanoparticles. Gold nanoparticles, for example, can exhibit structural hysteresis, where the atomic arrangement depends on thermal history. Gold nanoparticles can exist in multiple structural phases, such as face-centered cubic or icosahedral. The specific structure adopted can depend on the thermal history, creating structural memory. Surface reconstruction, where surface atoms rearrange to minimize energy, creates additional energy barriers that can trap the system in metastable states. To understand this more quantitatively, let's write down the free energy expression for a nanoparticle. The Helmholtz free energy F equals internal energy E minus temperature times entropy S. At low temperatures, the energy term dominates, and the free energy is approximately equal to the internal energy. The system sits in the lowest energy configuration it can find. At high temperatures, the entropy term becomes important, and many different states become thermally accessible. The system explores a larger portion of configuration space. When considering a transition between states, delta F equals delta E minus T delta S. Interestingly, memory can arise from entropic barriers as well as energetic ones. Some transitions require the system to pass through configurations with reduced entropy, creating an effective barrier even if the energy landscape is relatively flat. To build intuition, let's discuss some analogies. The first is spin glasses. Spin glasses are magnetic materials with disordered, competing interactions that create a highly frustrated and rugged energy landscape, very similar to nanoparticle systems. In a spin glass, neighboring spins want to align in contradictory ways due to competing ferromagnetic and antiferromagnetic interactions. This creates frustration and many nearly degenerate states. Spin glasses exhibit aging and memory effects that are remarkably similar to those in nanoparticles. The system remembers the temperature at which it was aged. Both spin glasses and nanoparticle systems respond to temperature cycling protocols in characteristic ways, showing rejuvenation when heated and memory recovery when cooled back to previous temperatures. Another beautiful analogy comes from protein folding. Proteins must navigate incredibly complex, rugged energy landscapes to reach their native folded state. Like nanoparticles, they can get trapped in misfolded configurations. A protein chain must explore conformational space to find its native structure. The pathway is not straightforward, and proteins can get kinetically trapped in intermediate states, just like nanoparticles. Interestingly, cells use chaperone proteins to help other proteins fold correctly. These chaperones are analogous to careful annealing protocols used to help nanoparticles reach desired configurations. Misfolding diseases like Alzheimer's occur when proteins get trapped in incorrect configurations. This is directly parallel to structural memory in nanoparticles, where the system remembers and preserves a non-equilibrium structure. A third powerful analogy is the glass transition in supercooled liquids. When you cool a liquid rapidly, it can form a glass, which is essentially a liquid frozen in a non-equilibrium state. The glass structure depends on the cooling rate, exhibiting memory of the thermal history. Near the glass transition, the relaxation time follows a Vogel-Fulcher-Tannen law, tau proportional to the exponential of A divided by T minus T0, where T0 is the Vogel temperature. As temperature approaches T0, the relaxation time diverges and structural relaxation becomes impossibly slow on experimental timescales. The system is effectively frozen with structural memory intact. Nanoparticles near their blocking temperature behave remarkably like supercooled liquids approaching the glass transition temperature. Both show dramatic slowing of dynamics and memory effects. How do scientists actually observe these memory effects experimentally? In magnetic nanoparticles, a standard technique is to measure zero field-cooled versus field-cooled magnetization curves. The difference between these curves reveals blocking behavior and memory effects. This shows schematic magnetization versus temperature curves. The zero field-cooled curve increases with temperature up to the blocking temperature, while the field-cooled curve is higher and relatively flat. AC susceptibility measurements at different frequencies can map out the distribution of energy barriers in the system. The peak position shifts with frequency, revealing the dynamics of barrier crossing. Sophisticated temperature cycling protocols can demonstrate memory. You cool the system with stops at specific temperatures, then heat it back up. The system shows signatures of remembering the stop temperatures. Thermoerminent magnetization, where you measure the decay of magnetization after removing a field, provides information about the distribution of relaxation times and energy barriers. These memory effects aren't just scientifically interesting, they have important technological applications. Understanding and controlling memory effects is crucial for magnetic data storage. You want information to persist for years, which requires very high energy barriers and long relaxation times. In catalysis, nanoparticle catalysts can show memory of their activation history. The catalytic activity can depend on how the nanoparticle was prepared and treated, reflecting structural memory. In drug delivery applications, nanoparticles can be designed with memory effects to control release rates based on thermal history, allowing for sophisticated release profiles. In emerging quantum computing applications, protecting quantum states requires understanding and mitigating unwanted memory effects that can cause decoherence, while exploiting desired memory for information storage. Let's develop a more rigorous theoretical framework using the master equation approach. The time evolution of the probability Pi of being in state I is given by d Pi over dt equals the sum over j of Wij times Pj minus Wji times Pi, where Wij is the transition rate from state j to state I. The transition rate Wij equals nu0 times the exponential of negative E barrier from j to I divided by kBt, where nu0 is an attempt frequency. At equilibrium, detailed balance requires that the forward and reverse rates are related by the Boltzmann factor of the energy difference between states. Specifically, Wij divided by Wji equals the exponential of negative quantity Ei minus Ej divided by kBt. When you solve this master equation, you find that the system has a spectrum of relaxation modes. Memory effects emerge from the slowest modes, which correspond to transitions between states separated by high barriers. Here's an important practical question. Can we prevent or erase memory effects when we don't want them? Yes, memory can be erased through carefully designed thermal protocols. The key is providing sufficient time at high enough temperature for the system to fully equilibrate. The annealing time must significantly exceed the relaxation time of the slowest mode. If tau is 100 seconds at your annealing temperature, you need to anneal for thousands of seconds to ensure equilibration. The annealing time must be much greater than tau max, which equals tau 0 times the exponential of E max divided by K B times T anneal, where E max is the highest barrier you want to overcome. Additionally, using very slow cooling rates allows the system to remain close to equilibrium throughout the cooling process, minimizing memory of non-equilibrium high-temperature states. The memory effect shows a strong dependence on nanoparticle size, which is crucial for applications. Larger nanoparticles have stronger memory effects and higher blocking temperatures because their energy barriers scale with volume. Remember that EB is proportional to volume, which is proportional to diameter cubed. Below a critical size, typically a few nanometers, nanoparticles become superparamagnetic at room temperature with no memory on experimental timescales. The critical diameter is approximately equal to 25 kBt times the natural log of tau measurement over tau 0 divided by pi k, all to the 1/3 power. For magnetite at room temperature, this critical diameter is approximately 8 nanometers. Particles smaller than this show no magnetic memory at room temperature. Surface effects play a critical role in nanoparticle memory, especially for very small particles. Surface atoms have reduced coordination compared to bulk atoms. This creates a distinct surface energy landscape that can dominate the overall behavior in small nanoparticles. The surface fraction is approximately 6T over d, where T is the surface layer thickness, typically 1 or 2 atomic layers, and d is the particle diameter. For a 5 nanometer particle with a surface layer of 0.5 nanometers, approximately 40% of the atoms are surface atoms. This huge fraction means surface effects completely dominate the behavior. In magnetic nanoparticles, surface spins often form a disordered shell with frustrated interactions. This surface disorder creates additional energy barriers that contribute to memory effects. When nanoparticles are in close proximity, collective effects can dramatically modify memory behavior. Magnetic nanoparticles interact through dipole-dipole interactions. These long-range interactions couple the dynamics of neighboring particles. The dipolar energy is proportional to mu1 times mu2 divided by r cubed, where mu1 and mu2 are the magnetic moments and r is the separation. In dense assemblies, these interactions can cause particles to block collectively at higher temperatures than they would individually. The ensemble acts as a coupled system with emergent memory properties. Very dense nanoparticle systems can exhibit superspin glass behavior, where the particle moments act like spins in a spin glass. This creates extremely complex memory effects with very long relaxation times. The memory effect in nanoparticles is a beautiful example of non-equilibrium statistical mechanics. The fundamental issue is violation of ergodicity. In equilibrium statistical mechanics, we assume the system explores all accessible states given infinite time. But nanoparticles violate this on experimental timescales. The experimental time t express is much less than the ergodic time tau ergodic needed to fully explore configuration space. The system is effectively confined to a limited subspace of the full configuration space. Which subspace it occupies depends on history, creating memory. This leads to concepts like aging, where properties change slowly with time even at constant temperature, and effective temperature, where different degrees of freedom have different apparent temperatures. Let me conclude by discussing recent developments and open questions in this field. Recent work uses machine learning to predict how memory effects will manifest based on particle characteristics and thermal history. This could enable precise control of memory for specific applications. New experimental techniques allow measurement of individual nanoparticles rather than ensembles. This reveals heterogeneity in memory behavior that was previously hidden by ensemble averaging. In the smallest nanoparticles, approaching molecular sizes, quantum effects become important. How classical memory effects transition to quantum behavior is an active area of research. Researchers are exploring non-thermal methods to control memory, such as using light, electric fields, or mechanical stress. This could enable manipulation of memory without heating, avoiding thermal damage. A fundamental open question is whether we can ever achieve complete reset of memory in finite time, or whether some trace of history always persists at the molecular level. Let me summarize the key points about the Nanoparticle Memory Effect Paradox. Memory effects arise fundamentally from the rugged energy landscape of nanoscale systems, with multiple metastable states separated by high energy barriers. The exponential temperature dependence of relaxation times means that modest temperature changes can shift timescales from seconds to years, or vice versa. Memory behavior depends critically on particle size, surface effects, and interparticle interactions. All three must be considered for accurate predictions. The practical implications span diverse applications, from magnetic data storage to catalysis to drug delivery, wherever control of nanoscale states matters. The phenomenon connects to broader themes in condensed matter physics, including glass transitions, protein folding, and spin glasses, revealing universal aspects of complex energy landscapes. Understanding, predicting, and controlling memory effects in nanoparticles remains a frontier challenge, combining statistical mechanics, materials, science, and practical engineering.